Hi everybody. So this was requested from homework 10E or chapter 10, problem 40. So it basically goes as follows. A cyclist is coasting at 12 meters per second. So there you go there. When she starts down a 450 meter long slope that is 30 meters high. So 450 meters is kind of the distance traveled, where the height from the slope is 30 meters. The cyclist and her bicycle have a combined mass of 70 kilograms. A steady 12 Newton drag force due to air resistance acts on her as she coasts all the way to the bottom. What is her speed at the bottom of the slope? So we're trying to find out her speed at the bottom of the slope. All right. So I think what I'm going to use is the work energy theorem here. So basically there's going to be work done by this drag force here. So I'm going to say work done by the drag force is going to equal the change in energy of the system. And the system is going to be essentially the cyclist with their bike and the earth and all that. So yeah, all right. So with that said, then the work done by the drag force is going to equal the change in energy of the system. That basically means, well, there's two types of energy. So I'm going to say this here is my initial moment. This is my final moment. And at my initial moment, the type of energy I have is gravitational potential energy. And I've also got kinetic energy. And then if I consider this to be my zero mark, so that's going to be 0, my energy at the end is really just going to be kinetic energy. And then some work is going to be done by this drag force taking mechanical energy out of the system. So I think I'm just going to say that the total energy is really just the sum of the changes in energy. So like this change in energy, right? So if I just say kind of like the sum of the changes in energy, that's going to be essentially the change in kinetic energy plus the change in gravitational potential energy. So I just add up all the changes in energy. So what does that look like here? Well, that's going to be the change in kinetic energy plus the change in gravitational potential energy. So the work done, again, by the drag force is going to be the kinetic energy. So that's going to be the final kinetic energy minus the initial kinetic energy plus the final gravitational potential energy minus the initial gravitational potential energy. But right at the end, there is no gravitational potential energy because I made my 0 mark here. So this becomes 0. So now I have the work done by the drag force is going to be the final kinetic energy, so it's 1/2 mv final squared, minus the initial kinetic energy, 1/2 mv initial squared, and then I'm going to subtract because I got still have this negative right here. So it's going to be minus mg times my height, my initial height, which I could consider this to be my initial height right here. Let's see, and I'm trying to solve for this final speed right here. And I think I know everything, so now I really just need to do, I'm going to isolate that v final, but I still need to unpack this drag force here. So that drag force, well, it's going to be, they told me it's constant, so it's basically going to be that drag force 12 newtons. So it's the work in general. The definition of work is the force times the distance, or the displacement, times cosine of the angle between the force and the displacement. So, and I'm going to plug that in there. So that's going to be the drag force itself multiplied by the displacement, which is d, times cosine of the angle. Well, the displacement kind of points down and to the right here, where the drag force is going to point up and to the left. So the angle between these two vectors, the displacement and the drag force, is 180 degrees. And that's going to equal 1/2 mv final squared minus 1/2 mv initial squared minus mg h initial. So cosine of 180 is -1. So that's going to be negative drag force times the displacement equals all this stuff, 1/2 mv final squared minus 1/2 mv initial squared minus mgh initial. So now it becomes a lot of math, basically. Let's see, I think I'm going to start with just multiplying everything by 2. I think that's going to make my life a little bit easier. So I'm just going to multiply both sides by 2. So that's going to give me -2 times the drag force times the displacement is mv final squared minus mv initial squared minus 2mgh initial. And then add both of these to both sides, so plus mv initial squared plus 2mgh initial. So plus mv initial squared plus 2mgh initial. Cancel, 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 cancel. So this now becomes mv initial squared plus 2mgh initial minus 2 times my drag force times the displacement is mv final squared. So I'm going to divide by mass and take the square root. So that's going to be mv initial squared plus 2mgh initial minus 2 times the drag force times the displacement divided by mass, and then I take the square root, and that's going to be my final velocity. So let's see what all that looks like in terms of numbers. So mass, I think, is 70 kilograms. Yep. So it's going to be 70 multiplied by the initial speed, which is 12 meters per second, squared, plus 2 times 70 times g is 10. Initial height is 30. Minus 2 times the drag force, which I believe is 12, times the displacement there. It's a bigger displacement, so it's 450 meters. All that's under the square root here. Let's just square root equals v final. And then we just divide it by the mass, which is 70. So I got to plug all this into my calculator. Let's see what that looks like. And then we'll see what the final speed is. So 12 squared, that's 144 times 70. Plus 2 times 70 times 10 times 30. And all that minus 2 times 12 times 450. Divided by 70, and then we take the square root, and I'm getting 24.3. And there we go. So hopefully that helped. All right. Bye.